Today we're going to get started on a very important topic, which is called optimization. Optimization is basically mathematical min-maxing. Your objective is to get the best. What the best means is different from situation to situation. But you want the most, or you want the least. You want the highest profit or the lowest cost. You want the best quality of life, the best sleep, that kind of thing. So we're going to study between today, tomorrow, and the next few days how to approach a problem like that from a mathematical point of view. We're going to start by introducing some relevant terminology: local maxes and mins, global maxes and mins, and critical points. Then we're going to practice finding those things on a graph, and then we're going to practice finding the global maxes and mins of a function on an interval. So just to set the stage here, suppose that, some psychologist or sociologist has done some study and they found that there is a graphical relationship between a person's overall health and well-being as measured against the number of hours of sleep they get each night. If a person is getting no hours of sleep each night, they are basically deceased. 0 overall health and well-being. Likewise, if they're getting 24 hours of sleep per day. The highest level of overall health and well-being is achieved right around this peak here, which corresponds to, roughly speaking, 7-8 hours of sleep, as we have been told, right? The quote-unquote ideal situation corresponded to the location where this graph was at its highest. So we have mathematical terminology for these points where the graph is at its highest or at its lowest. A local minimum is a point which is lower than all nearby points. Local because it's the lowest point in its neighborhood. Local maximum, conversely, is a point which is higher than the points all around it. Higher than all the other points in the neighborhood. A global minimum is lower than every other point, period. Likewise, a global maximum is a point which is higher than all other points, period. So let's quickly go ahead and make this concrete with an example. Let's have a look at the graph given here and let's identify the locations of all the local maxes, all the local mins, all the global maxes, and all the global mins. Looking at this graph, for the global max, which point is higher than all the other points on the entire graph? It seems to me that the global max is located right here. I'll call this point A for short. This point is higher than any other point on the graph, therefore it is the global maximum. What about global minimum? Which point on the graph is lower than any other point in the picture? I think that global minimum is located down here. The graph never falls below this point. So I'll call that point B for short. Point B would be the location of a global minimum. The local maxes don't have to be higher than any other point. They just have to be higher than any nearby point. Now, one thing that I'm noticing is that the point called A, the global maximum, was also a local maximum. If it's higher than every other point in the entire picture, then it's certainly going to be higher than any other point nearby. However, it's not the only local maximum. There is another point which is king of its little town, and that's the point given right here at this sort of V-shaped location. This point, which I will call C, is certainly higher than every other point nearby. Move a little bit to the left or move a little bit to the right. In either case, you find yourself moving down. Now the next point that draws my attention is this location on the far left side of the graph. This point located right here. By the definition, it does seem like this point would qualify as a local maximum, because that endpoint is certainly higher than every other point nearby. But when we're talking about local maxes and local mins, there is one tiny technicality, basically just a convention. Technicality/convention, endpoints of a function don't count as local maxes or local mins. They are allowed to be counted for global maxes and mins, but they're not allowed to be counted as local maxes or mins. Now, anytime there is a convention, anytime there is a technicality like this, it's usually just because if you and I agree that local maxes and local mins can't be endpoints, it makes describing something or talking about something later on more convenient. So this exists for the reasons of convenience, to make certain theorems easier and shorter to state. That's the reason for this convention. So what are our local maxes? Which points are higher than any nearby point? Only the points labeled A and the point labeled C. This endpoint isn't counted. Now let's check out local mins. Once again, the point labeled B was lower than any other point on the graph, and therefore was certainly lower than any nearby point. So the point labeled B also counted as a local min, but another local minimum is given by this point down here. Maybe I'll just call this point D. This point on the far right side would not be counted as a local minimum because it is at the right end of this graph. Now I want us to go back to that picture for a moment, and I want us to take a hard look at the locations of all the local maxes or local mins. Collectively, we would call them the local extremes, all the local maxes or mins. The points labeled B, D, and C, notice that at each of those locations, the graph is flat. The only exception to this is the point labeled C, which has its own kind of weird property. The graph isn't flat at C, but the graph does have a corner at C. So all the local extremes, point A, C, B, and D, were located at points where either graph is flat or the graph has a corner. A global extreme, a global max/min, can be located at a point where either the graph is flat or the graph has a corner, or at one of the ends of the graph. The endpoints can't be counted as local extremes, but an endpoint can be counted as a global min or a global max. So imagine that you are analyzing a graph and you want to achieve the absolute best, whatever the best means in your scenario. The best is going to be located at the global max or at the global min. So if you're looking for a global max or for a global min, you only have to look in basically 3 different locations. You have to look at locations where the graph is flat, locations where the graph has a corner. In either of these 2 cases, you're looking at a local extreme. Or you're looking at an endpoint of the graph. The best case scenario is going to be located at one of these 3 points, where the graph is flat, where the graph has a corner, or where the graph has an endpoint. So we give a special name to the locations where f of x could have a global extreme. A critical point of a function called f of x is a point where either f prime of x, the slope of the tangent line, is 0, or f prime of x is undefined. Scenario number 1 covers the case where the graph is flat. Scenario number 2, it turns out, covers the case where the graph has a corner. I'm not going to go into exactly why that is in this video. If you're curious, you can watch my optional video on differentiability, which I will try and put a link in the video somewhere to that. A global extreme can only be found at really one of 2 locations, either at an endpoint or at a critical point. So when you're looking for the best, mathematically speaking, you take your function, you list all the critical points, you list the endpoints, and then you try and figure out which one gives you the optimal result. So let's practice mathematically finding the critical points of the function x cubed minus 6x squared plus 3x plus 7. Oops, and I've forgotten an important extra little bit here that is really going to make this problem feasible. Let's just find the x coordinates. Of all the critical points of this function, we won't worry about the y coordinates of the points, just the x coordinates. Critical point. By definition, when we're looking for critical points, we're looking for locations where either f prime of x is equal to 0 or f prime of x is undefined. To stand a chance at investigating either one of these possibilities, we should probably work on finding f prime of x. This is a polynomial, so this isn't so bad. We've got 3x squared minus 2 times 6, 12x, plus 3. And looking at this, I can tell that this function will never be undefined. If I'm going to get any critical points out of this function, they're all going to come from the first possibility, points where the graph is flat, points where f prime is equal to 0. So I'm going to take f prime and set it equal to 0. And in solving this, I might simplify this equation a little bit because it looks like all of the different terms contain a factor of 3. So this would be x squared minus 4x plus 1. Now, looking at this expression on the left side, I don't think that this can be solved by factoring, but we can always use quadratic formula. The exact values of x would be negative b plus minus the square root of b squared minus 4 times a times c all over 2 times a. So it looks like 4 plus minus root 12 over 2. I think you can simplify that, but I'm just not going to bother, I think. So if I was working on a problem where I was trying to optimize this function, either find a global minimum or a global maximum, I would start by looking at these specific x values given here. These are the only two locations where it is possible to find a global max or global min. Now, in case you don't quite believe, we can always have a look at the graph, and sure enough, the only point on this graph which has the potential to be a global maximum is given by this local maximum right here. This point is higher than every other nearby point. And this corresponds to the solution that has a minus sign. Likewise, the only potential candidate for a global minimum occurs right here. The issue, though, is that although these 2 points are candidates, although these 2 points are reasonable locations to try and look for a global max, global min, none of these points are guaranteed to actually be equal to a global max or a global min. And as a matter of fact, this function does not have a global max. This function does not have a global min. Because depending on the size of the x value that you plug into the function, you can get y values of unlimited height. It's not possible to have a single point which is higher than every other location on the graph, because the graph can get infinitely tall. Likewise, this bottommost point was a candidate to be a global minimum, but it was not the actual global minimum. This function does not have a global minimum. So when you're working on a problem and you've calculated the critical points of a function, how can you tell what that critical point actually represents? Is the critical point a local min or a local max? Or is it potentially the global min or the global max? Option 1, of course, is just to graph the function and have a look at the graph of the function. That is definitely the most reliable way, generally speaking. But the real issue with this method is that quote-unquote look at a graph are not instructions that you could give to a computer. This isn't a process that you could automate or program. So when we are trying to use machines, when we're trying to use computers to do tasks for us, there's this huge hurdle of taking something which is intuitive to us as humans and changing it into something computational and concrete that a computer can understand. I remember just a few years ago going to a conference, and a researcher was giving a presentation. They were trying to make a machine that could be used to harvest strawberries. And their machine could move fine. Their machine could spot a strawberry, but the machine was having trouble finding the stem of the strawberry so that it could cut the stem and harvest the berry. So the researchers were in the middle of a years-long process of trying to figure out how to articulate to a computer what a strawberry stem looks like. And likewise here, it's very difficult to communicate to a computer what it means to look at a graph and see from the graph whether you have a local min, local max, global min, or global max. So we are very, very lucky in this situation. People from hundreds and hundreds of years ago have developed 2 tests that can be used to mathematically determine through calculations whether the point that you're looking at is a local min, local max, global min, or global max. And that means that this is something that can be done by computer. This is something that could be programmed, automated. Now in the previous example, we saw a function which did not have either a global minimum or a global maximum. The graph of the function could get infinitely low and likewise infinitely high. However, if I took this function and I decided to impose some ends on this graph, all of a sudden this function does have both a global min and a global max. The global min, the point that's lowest in this picture, is the point indicated right down here. The global max, on the other hand, in this case, is located at an endpoint. This wouldn't be a local maximum, but it does count as a global maximum. So here's a theorem for you. Suppose you have a function which is continuous, remember that word, continuous on a closed interval AB. So this goes all the way back to video, I think 4 or 5. Continuous on a closed interval AB. You can draw the entire graph from x equals a to x equals b without ever lifting your pen. If you consider the function only on the interval AB, has both a global max and a global min. So let's consider the following exercise. Let's find the global maximum and the global minimum of the function f of x equals x plus 1 squared times x minus root 17 squared on the interval 0, 2. Give exact values. Because we have restricted our attention to the interval from 0 to 2, f of x must have a global max / global min among all the points in that interval. So I know in advance that it is possible to find a global max and a global min. The second thing I know is that there are limited locations where a global min or max could possibly be found. We could find them at a critical point, which was a point where either the graph was flat or the graph had a corner, or a global min max could be found at the endpoints. In this case, could be found at either x equals 0 or x equals 2. So the first thing that I'm going to try and do is figure out the critical points of the function. Once I've found the critical points and I have the endpoints, I will now know all the possible locations where a global min / global max could be found. So we're going to need f prime of x. And to find it, this is a great opportunity, I think, to use the product rule. X plus 1 squared times the derivative of x minus root 17 squared plus x minus root 17 squared times the derivative of x plus 1 squared. Can you guys hear that dog barking? Hold on. So now let's find these derivatives using, for example, chain rule. So the first we have x plus 1 squared, and then we have the derivative of the outer function, 2 times blank, and then multiply that by the derivative of the inner function. But it looks like the derivative of x minus root 17 is just going to equal 1. X will become 1 and the constant will vanish. Then we have x minus root 17 squared times the derivative in the back, 2x plus 1, and then once again, similarly, the derivative of the inner function is just 1. It really doesn't affect anything. Now, I absolutely do not want to expand this. I don't want to multiply all of this out. What I'm going to do actually right now is factor this as much as I can. For example, I'm noticing that both of these two terms have a factor of 2. Likewise, both of these terms have a minimum of 1 factor of x plus 1. And both of these terms have a minimum of 1 factor of x minus root 17. So if I factor all of that out, what's left? From the first term, I took the 2 and the x minus root 17, and I took one of these x plus 1s. So the only thing that will be left is that extra x plus 1. And over here, I took the 2 and the x plus 1 and one of these x minus root 17s. So only one of those x minus root 17s will remain. So, simplifying this a little bit further by combining like terms, x plus x is 2x, and then plus 1 minus root 17. Let's consider where f prime would be equal to 0, or f prime is undefined. But because we don't have any square roots containing variables, we don't have any fractions, we don't have any logarithms, this quantity is always defined. So that begs the question, where is this quantity equal to 0? And because we left this factored, we can now solve this equation using the zero product property. To say that either the x plus 1 is equal to 0, or the x minus root 17 is equal to 0, or the 2x plus 1 minus root 17 is equal to 0. So x could be equal to minus 1, or x could be equal to root 17, or x could be equal to root 17 minus 1 over 2. So at this point, we have obtained 5 possible locations for the global max and global min. These 3 critical points, as well as these 2 endpoints, 0 and 2. However, I think that we can immediately eliminate 2 of these possible locations. I think 2 of these x values disqualify themselves, namely x equals -1 and x equals root 17. The issue is that these 2 x values are actually outside of the interval 0, 2 that we're concerned with in this problem. So actually there are really only 3 possible locations where the global max and global min could be found. The left endpoint, x equals 0, the right endpoint, x equals 2, and the one critical point that didn't get disqualified, root 17 minus 1 over 2. Of these 3, how will we tell which one of these is the global min versus the global max? And as usual, there are 2 possible ways. One of them is very concrete, very mathematical, very calculation heavy, which is absolutely perfect if you need to program that into a computer. And the other method is a little bit more intuitive, a little bit more human. So the human technique would be to just graph the function and to look at the graph and see what's going on. Here's the graph of the function as restricted from 0 to 2, and graphically what we can see is that the global minimum the lowest point, is located at the endpoint x equals 0, the left endpoint. We can also see that the global maximum is achieved at this location right here, where the graph is flat. And just by process of elimination, it makes sense that this would be square root 17 minus 1 over 2. And you can check by finding a decimal approximation for that value to see if it actually matches this 1.562 given here. So from the graph, we saw that the global min on the interval 0 to 2 was attained at x equals 0, and the global max was attained at the critical point x equals root 17 minus 1 all over 2. But what if you were going to do this in the more computational way? A way that didn't rely on the human intuition of looking at a graph. The other way, which is more conducive to calculation, is just to go ahead and calculate f evaluated at x equals 0, f evaluated at x equals 2, and f evaluated at x equals square root 17 minus 1 all over 2. See what the output values are. I've gone ahead and done those calculations off screen. F of 0 produces 17, f of 2 produces 40, and f of the critical point produces 43. So the lowest y value corresponds to the global min. The highest y value corresponds to the global max, which matches what we saw graphically. So if you were programming a computer to do this, you would just have it evaluate the function at all the different candidates, the endpoints and the critical points, and you would have it compare the sizes of the outputs. The smallest output gives you the global min, and the largest output gives you the global max. That concludes today's material. We introduced some vocabulary: local mins, local maxes, global mins, and global maxes. We noticed that global maxes and global mins in particular were located at locations where either the graph was flat, or the graph had a corner, or at the endpoint of an interval. The locations where the graph was flat or was undefined were called critical points, and therefore if we're looking for global mins or global maxes, we only have to look for critical points and endpoints. What is the function doing at those locations?